Welcome back for a new season of the Below the Surface podcast. I'm your host, Gunnar Hyde. My co-host, James Hammond, will be with me in the interview. The reason why he's not in this introduction is because I recorded this introduction and I screwed up the audio file, so I do it alone really quickly. Today we are talking to Professor Albert Juhasz. She's a research professor at the Futures Industries Institute in Adelaide. He's a widely recognized and heavily cited researcher on bioavailability and human health exposure. Albert has led the development of one of the world's largest contaminant bioavailability databases. He has also worked on our famous NEPM, on our National Environmental Protection Measure. He has contributed to the N-Health guidelines. He has influenced regulatory guidance in the United States, Canada, and New Zealand. He's a senior journal editor, a World Health Organization consultant, a contaminated site auditor advisor, and he is a highly cited researcher with an H index. You can look that up. That's actually a very cool thing. The H index, he has an H index of 37. So join James and me for this chat with Dr. Albert Juhasz. We're going to get into bioavailability and bioaccessibility, what the difference is, and how we as contaminated sites consultants can make use of a certain knowledge of how contaminants actually make their way into the bloodstream to write probably some better report. Oh, and before I forget, during the interview, Albert mentions the term assay. And before I started looking into bioavailability as a preparation for this interview, I had never heard of this term, assay. Basically, it is substituted with a testing methodology if you haven't heard of it before. So here we go. Albert will introduce himself. Enjoy it. James and I certainly did. Albert, how are you?
I'm very well. How are you?
Albert, this is Hammond, James Hammond.
Hey, Albert.
G'day, James.
Albert, we always start off asking our guests, say someone comes along, some Hollywood producer, and says, man, I mean, your life has just been riveting. We got to make a movie out of this. And you can pick the actor. Which actor would you like to play you?
Oh, gee, that's a hard question to answer.
I mean, we have a few, because scientists aren't often the ones who star in movies. So Cillian Murphy, of course, in Oppenheimer would be a good one, or Matt Damon in The Martian. One of my favorites would be Russell Crowe as Dr. Nash in A Beautiful Mind. Or you could pick Jodie Foster, right, as in Contact.
Maybe Liam Neeson. He might play a good scientist role, maybe.
As in Taken 1 and Taken 2.
Yeah, why not? Take all of them.
He's pretty versatile, Liam Neeson, actually, isn't he? He's actually got quite a bit of range.
Yeah, absolutely.
Yeah,
absolutely.
I could see that.
Could you introduce yourself to our listeners, please, Albert?
Hi, I'm Albert Juhasz. I'm a research professor at the Future Industries Institute at the University of South Australia.
And your main topic of research is understanding of how much contaminated soil, be it soil dust or food, is actually absorbed in the human body. Is that a fair summary of many, many years of work?
Yeah, that's a fair summary. Like the majority of my research over the past 20 or 25 years is looking at bioavailability issues associated with human exposure, predominantly through incidental soil ingestion pathway. So it's trying to come up with methods that can better quantify bioavailability, trying to understand factors that influence bioavailability, and then also extending that through to development of different strategies to minimize exposure through bioavailability adjustments.
Mm-hmm. How did you end up in that? What triggered your interest in that?
Oh, look, I've been working in environmental contaminants for a very long time. So stemming back to my honours degree and my PhD, And the early work that I was doing at CSIRO was in the remediation of contaminated environments program. So within that program, we looked at different remediation technologies, but we also started looking at what was actually driving exposure. So that was back in the very late 90s, early 2000s, where we started playing around with some bioaccessibility tests, trying to estimate what exposure may be through that incidental soil ingestion pathway.
Mm-hmm.
Albert, you just mentioned another word there, bioaccessibility. Are you able to explain the difference between those two terms, bioavailability versus bioaccessibility? They are different, am I right?
Oh, absolutely. And sometimes, the terms bioavailability and bioaccessibility are used interchangeably. Bioavailability is the fraction of the contaminant following exposure that is actually absorbed and reaches the systemic circulation or reaches the bloodstream. Whereas bioaccessibility is the amount that is potentially available for absorption into the bloodstream.
What's of primary concern to us environmental consultants would be the bioavailability, because that's what actually makes it into the bloodstream and can cause harm. It's not something that is theoretically accessible to us.
Definitely. So trying to understand what that bioavailable fraction is, that may have a significant impact when you're refining your exposure parameters and then detailing what the risk may be associated with that exposure. The issues with bioavailability assessment, those types of assessment tools aren't readily available to environmental consultants or general population as well. So that's where bioaccessibility research came in, understanding that there are ethical issues associated with running animal tests and whether or not you can develop a simple, rapid, inexpensive methodology that can predict what that bioavailable fraction may be.
Okay, let's face it, this is seriously important for us environmental consultants, because if we look at our NEPM, our National Environmental Protection Measure, they give us very nice health investigation, health screening levels for various contaminants that we religiously apply and look at. And as soon as things exceeded the various actions are taken or should be taken, very rarely do I see, I do see it in high quality, very expensive assessments. I do see that consultants then actually go, hang on a second, hey, we have X milligrams per kilogram of a certain contaminant in a sample. What does that actually then mean for this particular site use or for the site users? In the NEPM, where these guideline levels were developed and derived, maybe you should give us a quick rundown on at least the theoretical exposure scenarios that were assumed when the council came up with these HILs and these threshold levels, and what were the bioavailability percentages that were assumed.
Yeah, look, my understanding of the NEPM is that it's quite the HIL values are quite conservative. So they should be in terms of a first screen when you're doing initial investigations. So for the majority of contaminants, the assumption for the bioavailable fraction is that it's all bioavailable. So if you're exposed to that contaminated soil, then whatever is in the soil will be taken up and will be absorbed into the bloodstream. And in some cases that may be true, but I'd say for the vast majority that it is a conservative assumption, which then provides an opportunity to, go into a tier 2 risk assessment where you can refine your exposure parameters. And one of those exposure parameters may be an assessment of bioavailability, or more commonly utilised bioaccessibility for predicting that bioavailable fraction.
So the HILs that we use are conservative. We all know that. That's why they are tier 1 assessments, and they're only trigger values for further investigation. That's what they are supposed to be. But they assume a 100% bioavailability for almost all the contaminants. Is that okay conservative? Is this over the top conservative? How would you rate that?
Look, I think it's a good place to start. I think having conservatism in those initial screening values is appropriate. And as I said, there will be some sites where the bioavailability of the contaminant of concern will be high. If you're looking at urban lead or lead derived from paint or leaded fuels, often the bioavailability or the bioaccessibility of those is high. But on the flip side of that, there are equally enough cases where you might have lead that's derived from mining activities and where the mineralogy of the lead in that particular matrix will be such where the solubility under gastrointestinal conditions will be considerably lower. So, having that conservatism, I think, is necessary for those sites where the values are high, but you can always refine that. And running some of these bioaccessibility tests is quite simple. It's relatively inexpensive.
Also, is lead and arsenic, are both bioavailabilities assumed to be 100% in the NEPM?
The way that the lead value is calculated is a little bit different, but essentially there are some conservative assumptions in there. But certainly, if you want to refine those assumptions, then a similar type assay can be utilised that can get very good site-specific data.
But when you do get a HIL exceedance on a Tier 1 assessment, when does it make sense to take the step to looking at bioaccessibility or bioavailability as part of a risk assessment?
Yeah, look, great question. But for myself, I'm coming more from a research perspective. So trying to provide advice on what would be included or how things could be included into a Tier 2 risk assessment is a little bit outside of my remit. But my assumption would be that if there are other exposure parameters that can be modified suitably, then obviously go down those routes. And often, examples, if, it's a former gold mining source material, tailings, spoils, things like that, often the bioaccessibility will be quite low. So maybe as low as 20% or thereabouts.
It sounds like looking at the bioaccessibility of a contaminant can make sense perhaps where you've looked into other parameters and other assumptions that are going into a risk assessment and you feel the need to bring bioavailability in as well, or where the history or the provenance of the contaminant or the material you're dealing with suggests that it may have a low bioavailability.
Yeah, absolutely. There's some cases where you go, well, okay, it's a no-brainer. We know the history of the site.
Yeah.
We know those types of materials have been shown to have inherently low bioavailability.
You've mentioned a few times gastrointestinal analysis. We're talking about ingestion of a contaminant and going through the digestive system. Does your work around bioavailability also look at other pathways such as dermal contact and inhalation and bioavailability through those pathways as well?
Oh, absolutely. So, we have done some work on dermal absorption. So coming up with a surrogate method for predicting or estimating what a dermal absorption factor may be, particularly for polyaromatic hydrocarbons. And we've also done some work on inhalation exposure, again, for metals and metalloids. Inhalation exposure is quite difficult to assess.
Right.
One of the limiting factors associated with this type of research is to understand the relationship between the bioaccessibility outcomes that you generate using an in vitro test in the lab versus a bioavailability outcome that you generate following an in vivo exposure. We've done a lot of work utilizing some animal models for arsenic and lead. So we have a really good understanding of bioavailability using a number of different animal models for arsenic and lead. And so with that knowledge, we can then run our gastrointestinal extraction methods and then look at the relationship between the data we get for the in vivo test versus the in vitro. So trying to come up with an inhalation exposure approach that you can validate using an in vivo system is quite difficult. Similarly for dermal work, but we do know that if we are running the in vitro assays, it is a conservative estimate.
So just to clarify the two terms in vitro and in vivo, as I was researching the subject, these two came up. I didn't really know the difference. Give it to us in layman's terms.
Yeah. Okay. So if we're running an in vivo test, we're running an animal model, a mouse model, some rat studies. We've also done studies with juvenile swine. So we can administer our contaminated material to the animal of choice, and then we can monitor what the concentration might be in the bloodstream, what the urine excretion might be, or accumulation in different endpoints. It could be kidneys or liver. The in vitro is our chemical assessment tool, our tool that we can run in the lab. So it's running that artificial solution that we want to utilize or to represent that gastrointestinal system within our animal model.
All right. So one is theoretical. That's the in vitro one, is your simulation basically in the lab. And the in vivo is actually in life, right? Where you have some living organism that you expose to it to. Of course, it is vitally important to understand not only how much of a contaminant is there, which every environmental consultant does when you submit something to the lab. You get a number back and says, this is the concentration of a particular contaminant that's there. The next question should immediately be, all right, so how much of this is actually causing harm to the users or the environment? So in other words, if I get a sample back with 600 parts per million of lead, it could mean two totally different meanings depending on the type of lead that I have there and the type of soil.
Absolutely. So, just because the lead is there doesn't mean that it will be available for absorption. So there's a whole range of different things that can influence the solubility of lead for absorption into the bloodstream. There may be other things within the soil. The gastrointestinal system is quite complex, and you go from that, low pH that's in the stomach, but then as you transition into the small intestines, the pH starts to increase. And something like lead, between pH 5, pH 6, it's quite sensitive to precipitation events. There's other things that are in the soil, the iron content, it could be the presence of phosphate in there that can result in precipitation events, so that the amount that is remaining in solution in that intestinal phase, where it's the area or the sites where you do have absorption, may be significantly lower.
Another area where we see the word bioavailability used quite a bit is in sort of the supplement side of things. I would imagine there's a lot of work that's done in pharmaceutical companies and in supplement companies to understand bioavailability, with a goal of making things more bioavailable. Is there information that comes from that sector that is useful or applicable when it comes to looking at this from a contaminated land point of view?
Oh, look, the forerunners for the bioaccessibility tests that we run have come from nutritional studies. So going back to I think it was the 50s, where there was a whole range of nutritional studies that were developed to look at the bioavailability of iron in different foods. A whole range of different in vitro strategies, these gastrointestinal extraction methods, were developed more from a nutritional perspective. So, contaminated land assessment and bioavailability, bioaccessibility testing owes itself to both nutritional and also pharmaceutical studies.
Wow, amazing. I've been in this industry for so long, and I have not once even thought of running a sample for bioavailability. Not once. And this is highly, highly embarrassing. I only came across it lately because I have shifted more and more from immediately writing a remediation action plan when one of my or two of my contaminants exceed the tier 1 HIL, to hiring a proper risk assessment company or a risk assessor. And then suddenly the subject came up. It's like, well, and I read their reports and they mention bioavailability. I'm thinking, hang on a sec. Yeah, we have been missing out on something massively here. And, as a result of that, I came across your research, and I was referred to you. It's just amazing how such an important factor has been. I don't know if it's been ignored in our industry, but it certainly hasn't come across my desk. Let's put it that way.
We say it all the time that the numbers that we get in the ASC NEPM are great in one hand, in that they give us something like a kind of a common understanding of, of the starting point, but they're bad in the other, which is that whenever we have a number, there's this tendency to latch onto that. And even though they're not meant to be used as cleanup limits, they often are. Yeah, I'm with you, Gunnar. And I mean, I haven't been doing this anywhere near as long as you, but just in this conversation already, Albert, I've already learned so much. Remediating off the back of a tier 1 assessment and just going with a dig and dump strategy for remediation, it may be the best option in some cases, even if you could potentially go a little bit further and do a risk assessment. But I think that just having a really solid understanding of risk assessment and the work that, say, you do, Albert, with bioaccessibility and bioavailability is important, so that we can give people advice on what the options are and advise our clients what the best course of action may be.
And I can reflect on that. And like when we started doing this research back in the late 90s, early 2000s, we were generating a lot of information, and we published quite a few papers in the area. But then trying to get the word out to whether it was consultants more and regulators, auditors as well. And that evolution of presenting the information and having others sort of understand the concepts, because sometimes that concept of bioavailability and having an exceedance doesn't quite resonate, and understanding why there may not be any issue with that. So yeah, over the years we've run quite a few workshops in this area to try to get a greater understanding across the sector, to go, well, this is the concept of bioavailability, and it's not just associated with human health exposure, but also from an ecological perspective as well. But certainly it sounds like getting that information out more so would benefit the industry as well.
Here we go. In Sydney, our usual suspects, aside from all the petroleum hydrocarbons that everybody has to deal with, at least for the next few years until we get rid of them. But we have an awful lot of benzoylpyrene and polyaromatic hydrocarbons in our shallow fill layers, associated with unpleasant amounts of lead as well.
Yep.
Those are the usual suspects that we deal with. I do an assessment. I come across my usual suspects in the usual concentrations that are just above the HILs. And I want to know about how bioavailable is this. So how much of a soil sample do I cart where to find out?
Okay. So our 3 most common contaminants to undertake bioaccessibility analysis are probably lead number 1, arsenic number 2, polycyclic aromatic hydrocarbons number 3. And so if you had any of those contaminants or in any combination within a given sample, I would request to have a kilogram of soil sent per sample. And the reason why we ask for sort of a larger volume of soil is that we will process that, dry it, and then sieve it down to the less than 250 micron particle size fraction. And
what do you do with the rest?
What do we do with the rest?
Yeah, so you sieve it to the 250 microns. What happens to the other sample,
okay.
The rest of the sample?
Right. So we'll get a sample. First of all, we'll sieve it to 2 mils. And so for arsenic and lead, we'll determine concentration in the 2 mil fraction. So that can refer back to your site assessment. And then we'll sieve it down to the 250 micron fraction, which is utilised for the bioaccessibility assessment, because that's the upper size fraction that may adhere onto the hands of kids for incidental soil ingestion. Mm-hmm. The rest of the sample, if it's oversized, we discard it. We don't need to run it.
So you guys run a professional lab at the university?
Well, we've got our lab set up here. We've got all the facilities at the Future Industries Institute. We've got about $80 million worth of research infrastructure equipment. So whether we're talking about metals, metalloids, hydrocarbons, PAHs, we can run all that analysis. Now, for the bioaccessibility testing, they will do the gastrointestinal extraction method for both metals and for organics, predominantly PAHs. We've got a dermal absorption methodology for PAHs as well. So we'll run those assays and we'll generate samples or extracts from those assays.
When you've been talking about your in vitro gastrointestinal setup, I don't know if you've been to the MONA, which is the Museum of Old and New Art in
Yes.
Tasmania.
Yes.
They've got this model of the gastrointestinal tract, and it was a working functional model of the gastrointestinal tract. And it was, I mean, it's bizarre, but like I couldn't help it. My mind just went there when you're talking about it. But so please clear it up for me. Perhaps you could just explain for the in vitro gastrointestinal method. Could you just take us through like what's involved in that in particular?
I know exactly what you're talking about.
Yeah.
I went to MONA.
I imagine it's not like that.
Yeah, look, I've been to MONA a few times, and last year spent quite a lot of time just watching that whole thing. So the setup that we have is not like that. But I will say there are some in vitro methods that are similar to that, where they do have like microorganisms, and it's inoculated through fecal samples to look at food digestion and things like that. So particularly a group over in Belgium that run a particular method like that. Our method is far simpler than that, where we're not trying to replicate what's happening in the gastrointestinal system, but we're just trying to have some sort of measure that will be similar to what we get out from an in vivo study. So if we're looking at metals or metalloids, it's quite a simplistic system where there's a buffered system where it's buffered at pH 1.5. We utilize glycine as the base, acidified with hydrochloric acid. It simulates what may happen in terms of solubilization in a worst case scenario gastric environment. Running that gastric phase, it's all run in what we call a falcon tube. So it might be a 50 ml tube, it might be a 100 ml shot bottle, but we add in our soil at a solid to solution ratio of 1 to 100. When we then transition the sample after a period of time and after incubation to the intestinal phase, we then add in other constituents. We add in things that will contribute to the chyme. So it will be bile, pancreatin, it's a whole mixture of different enzymes. There could be surfactant-like materials that go in there. Again, it's at a concentration that is similar to what you might find in an organism. And then that is further incubated for a set period of time at 37 degrees.
Yeah, that's so interesting. I had no idea that sort of a method actually existed. I've just learned so much.
The important thing for us, particularly from the work that we did with in vivo and the in vitro assessments, is looking at that relationship between the two different assays, having the animal study as the gold standard. I was talking to an environmental consultant a while ago, talking about PAH, bioavailability and bioaccessibility. And they were saying, we had some samples run and the values were really, really low. I said, what type of assay did they run? Was it just a gastric phase extraction? And they said, yes. I said, well, that is not an appropriate assay to run for an organic contaminant, because the in vitro assay that you run for an organic contaminant is different. The composition and the makeup of that and the timeframes that you run it is different compared to an inorganic contaminant. So you need to understand what goes into the assay, how those constituents will influence the solubilization or the dissolution of your contaminant. and how that may relate back to the gold standard in vivo data.
When I send you a sample, you analyze it. What does the result look like? What do I get back? Is it a number, a percentage, or what's the report look like?
Okay, so the report that we send back will detail the concentration in that 2 mil or 250 micron fraction. So again, you can compare that back to your site assessment. We'll then provide data in another table where we've got the individual samples and we've run the in vitro gastric phase extraction. We'll give you the raw numbers that come out of that gastric phase, and that which will then utilise to calculate the gastric phase bioaccessible fraction in milligrams per kilogram. We'll have another table there that does the same if we transition that into the intestinal phase. And then we'll tabulate all the results where we've got the total concentration in that 250 micron particle size fraction, the gastric phase, the intestinal phase values in milligrams per kilogram, and then calculate the percentage bioaccessibility as well.
I don't know if I want to get into this or not, because when I send you a 1 kilogram sample, you throw out everything that's above 2 millimeters already, right? There's probably going to be, depending on the sample, but let's say there's 200 milligrams left of that 1 kilo sample. We have already, and that's not necessarily a problem with bioanalysis, but that's a problem in general. I send in a sample and the lab takes out stuff out of my sample. From that moment on, that's no longer my sample. That's no longer what I took away from the site. So somebody fiddled with my sample, and I am out there trying to obtain as representative a sample as I can. And the first thing that happens, somebody in the lab opens it and takes out some stuff. So I have a major problem with this process already, because the moment someone takes out 80% because it's too big, the grain size is too big, it's no longer my sample. And then I get results back. There's X parts per million lead in there. That is oddly enough not X parts per million of my sample. That is X parts per million of the one that was fiddled with. In other words, of the lower grain sizes, which we know inorganics and heavy metals attach to more than to the larger sizes, which someone has decided to take out of my sample. So the results that I get are not even results that are related to my sample anymore. They are related to an artificially increased concentration. Is this a valid complaint that I have here?
Well, it's an interesting thought. When an individual is exposed to a sample, there's a certain fraction that they're going to be exposed to. If we're talking about standard exposure via incidental soil ingestion, it's what is accidentally ingested. They're not deliberately trying to eat the soil. It's just a fraction that may stick onto their hands. And there's been numerous studies worldwide where they are looking at what particle size fraction actually sticks onto the hands. Mm. So in Australia, we use the less than 250 micron fraction. So that's why we sieve it down to that fraction. And yes, particularly when you're talking about lead, you're going to have most probably an enrichment in that smaller particle size fraction. And if you sieve that down to the less than 100 micron or less than 50 micron or 20 micron fraction, again, you might see that enrichment factor increase with those smaller particle size fractions.
Yeah, it would seem to me that perhaps particle size distribution of a starting soil sample is probably more important than maybe we think it is. You get the concentration of the oversized material. It's just that, and that's, going to be X milligrams per kilo, whatever it is. It's just that that's not relevant for what you then do, which is to look at the bioavailability in the smaller particle size. And I would imagine that a risk assessor would have to take that into account, in that, like, if the sub 2 mil fraction is 20% of the overall soil mass, then your bioavailability data really is only applicable to that 20% of the overall mass. I'm sure they would have to take that into account.
Yeah, or you could use some conservative assumptions associated with the bioaccessibility data. And
Yeah.
so, yeah, when we first started doing some of this work, we'd get a sample, we'd sieve it down, and then we'd get the concentration of arsenic or lead, for example, in that 250 micron fraction. And one consultant came back, how does that relate back to that 2 mil fraction? And go, well, okay, that's a really valid question. Let's include that into the report as well. So we do, for the inorganics, quantify what is in that larger particle size fraction or in the 2 mil fraction. What's in that smaller particle size fraction that we utilize for the bioaccessibility testing, provide the bioaccessibility data for that 250 micron fraction. In some cases, we have been asked to look at the particle size distribution within a given sample. And certainly in some cases, we've tested the bioaccessibility in different particle sizes from that bulk sample. So, yeah, if people are concerned with dust generation and what might be moving off-site, we can look at a smaller particle size fraction, sieve it down even further, quantify the total concentration, and then look at the bioaccessible fraction in there. So there's a whole range of different things that can be done. It's just having an understanding of how that information is utilised back into the risk assessment process.
This takes us down the rabbit hole that James and I have been going down ever since we started this podcast, where we staunchly claim that we are sampling wrong. The way how we take grab samples is not the way how to sample for environmental contaminants. It just isn't. Okay, there's so much research out there that we're kidding ourselves here. But I'm not starting that here now. Okay, so
That's good.
So I didn't even know that I can send samples to you. I thought I was going to talk to some ivory tower researcher who says, "Oh, well, send it somewhere else." So what's the classic example? I send you a kilo and say, Albert, I have PAHs in here. Guess what? And I also have lead in here. Here's my kilo of sample. In rough numbers, please, plus minus 100%. How much does one of these bioanalyses cost?
Yep. So if we're running a single element, we'll charge $660 a sample. So for arsenic, it's a simple gastric phase extraction, whereas for lead, we run the gastric phase and then we'll transition that into the gastrointestinal phase and generate data there.
And the PAHs?
For PAHs, the assay is a lot more complex. For PAHs, again, we do things in duplicate where we just quantify the concentration of less than 250 micron fraction. We'll then determine the bioaccessible fraction using our organic physiologically based extraction test. And for that, it's $1,100 a sample. We can also run dermal absorption, so looking at dermal bioaccessibility for PAHs as well. And again, that's another $1,100 a sample.
So say I have a site and I have 50 samples, especially those contaminants that we just spoke about. They are so heterogeneous across a site, and even not only across the site laterally, but they're also heterogeneous within my sample jar. They are just not equally distributed. Do you find that the bioavailability across a site varies a lot across a site, or am I okay with grabbing 1 or 2 samples and send them to you? You can already see where I'm going, because I don't want to spend 50 times $600 or $1,100.
Yes.
So how is the variability across a site?
Depending on source material, there may be some differences in terms of the bioaccessibility. However, the variability isn't huge. I often get asked, well, I've got this site, how many samples should I send? And I go, well, I don't know.
That was my next question.
Because I don't know anything about the site.
Yes.
And so I pose a question back to the individual and just say, look, if you can understand what variability lies on the site, and there may be differences in terms of concentration ranges in different areas, or you might have some visual differences in terms of what the soil looks like and what the profiles look like, then select an appropriate number of samples where you are accommodating the visual variability or the concentration variability and have those samples tested.
I am coming towards the end of my list of questions that I have. James, or sorry, I say Hammond, James Hammond. Anything else for you?
Oh, that was very enlightening, Albert. I learned more in the last hour than I had about this topic than I have in a long time. So a lot of this is about awareness. And I think if you were to run your workshop, for example, a lot of people who would attend, I would imagine, they're not looking to turn around and do this kind of work themselves, but it's the awareness that this exists, and it's the having it in mind that this is a relevant parameter to be thinking about when we're thinking about our sites. So like the more we can do that, I think the better we all become.
Yeah, absolutely. I can publish 100 papers and that's all great.
Yeah.
I get pleasure out of actually doing things that can impact the industry.
Yeah. It's putting it into practice.
Yeah. Even though we've been doing this for like 20 something years.
Yeah.
I still enjoy getting to the lab, running some of these little experiments.
Yeah.
It's standard approaches for us to do that, but significant value in terms of how the information is utilized and what cost savings the client may have in terms of not requiring remediation, or the risk management strategy might be reduced considerably because of the bioavailability implications.
Well, that's it. And, for a long time, we have looked at remediation. So, say a dig and dump remedial approach as not having a cost. But I think obviously more and more we're understanding that there is a significant cost with remediating sites unnecessarily, not just commercially, but also, in terms of carbon emissions and landfill space and a whole range of other issues. So yeah, I would like to think that your work would become more and more mainstream as we go forward, so that we can properly understand what our options are for assessing sites.
Yeah. Oh, definitely.
Thank you for joining us. It's been an incredible pleasure.
My pleasure.
Thanks, Albert.
Thanks, James. Thanks, Gunnar.
Bye.
Bye.